Start, sir.
Hi, welcome to the second live session of Irrigation and Drainage course. So, I am here, you can start asking questions. So, here my TA is with me, Shashank Shekhar, so he is going to take your questions, he is going to pass your questions to me and better ask the subject related questions. So, the last time I think we got some general questions, that is okay, but we expect you from the lectures. So, if you have any difficulty in understanding the concepts, you are not understanding the problems. So, maybe we can work on that here. So, if not possible this live session, probably the next live session we can answer some of the questions. Okay, so, we did not really receive any question during last I mean 3-4 days. So, we expect the questions live. Okay. All right. So, I hope you are enjoying the lectures. I think it's been 9th week, right? It's going 9th week is going on, and 9th week means we are in the drainage portion. So, we finished irrigation and also irrigation wells, and then the pumps section might have completed. So, I would like to introduce some things before you get any question. So, basically this water lifting devices we are talking about. So, that is some slides I think last week you might have studied. So, what are the lifting devices? Generally the lifting devices we are talking is lifting water from different sources. So, lifting devices are nothing but the devices that are really used to access water from different heads basically. So, okay. So, the lifting devices could be used to extract or access water from groundwater, from storage underground reservoirs, or from the rivers. So, okay. So, the three sources you can use these lifting devices to extract water or the lift water. So, these lifting devices are age old. So, since we are the age old civilization. So, there are several practices, lifting devices have been used long back, even the first century, even before that. So, the most, for example, water wheel or the swing basket. So, these are very old practices to lift water. So, and also the lifting water could be using the manual operated or animal operated or power operated like electricity, using electricity. So, that is why the lifting devices, the water lifting devices are classified into two main classes. One is indigenous class, in which the devices are used to lift the shallow depths basically. Okay. And mostly either is man or animal. So, that is indigenous. And whereas in pumps and the other category is the pumps. So, the pumps are being used using the electricity. Okay. So, there is a question, can you please explain what is the basic difference between effective porosity and drainable porosity? Okay. So, this is you might have studied during the drainage portion. So, in drainage basically the condition indicates the soil pores are filled with water, the completely filled with water. That means, the soil is saturated and due to that the any excess water you are putting on top or existing on top, that will be like standing, that will be like standing water. So, in drainage what happens, you are taking water, like withdrawing water from the ground, okay, withdrawing water from the ground. So, that means during the process you are taking water from the soil pores. Okay. So, that means you are lowering down the water table basically. Okay. So, suppose the water table initially at height h1, and after pumping or after withdrawing water from the ground, the water table is going lower to a height h2. Okay. So, in this the difference h1 and h2, the soil pores, the water which is present in the soil pores is being drained effectively due to gravity, okay, due to gravity. So, that is the soil has no force to hold this gravity water. So, due to gravity the water will freely flow. Okay. So, that water you are really capturing or withdrawing. So, that means here the drainable porosity. So, the pore space which is affected by this withdrawal is called the drainable porosity. Okay. And if you see, some pores are not really losing water. So, because of air entrapment or because of the void like tortuosity, some kind of thing. So, some water is not allowed to withdrawn basically. So, that means the pores are not participating, some pores are not participating in the flow process. So, because of that some water will be retained in the soil, and that is basically it is called effective porosity. So, if you have like total porosity, so some pores are participating in the flow process, that is called effective porosity, and the drainable porosity. So, that means the water which is withdrawn in 24 hours, if you see in 24 hours if you maintain. So, during the 24 hours, so the water which is coming from the drainage from the pores, which resulted from the filled pores, it is called the drainable porosity. And then the mostly the effective porosity what we are talking. So, that is the pores which are participated, okay, pores which are participated in the flow process, and then there is a, so it is effective porosity is less than the total porosity. Okay. So, the total porosity will be equal to effective porosity and the porosity which is not participated in the flow process. And then the question, another question, what are the different types of irrigation methods and which one is the best method? Okay. This is a different types of irrigation methods. I think we have explained in our previous lectures. Different types of irrigation methods, broadly classified into surface irrigation and the pressurized irrigation. Okay. So, this is the basic classification. Then after that there is a subsurface irrigation also. So, but in surface irrigation mostly we have like the furrows, borders, basin irrigation. Okay. So, these three methods we and also the flood irrigation. So, in case of that is a basin irrigation of course. So, furrows, borders and basins come under the surface irrigation, and then the pressurized irrigation. So, there is a sprinkler, a drip irrigation. So, because in case of surface irrigation, so water is freely allowed to the field by gravity. So, sometimes we also call it as a gravity flow irrigation, and then in case of pressurized irrigation. So, the water is pumped into the irrigation system, using some pumps, and then since the irrigation water needs to be cleaned, and if required there will be a filtering unit. So, the clean water can pass through the tiny pores in case of drip irrigation, and also in case of sprinkler irrigation. So, since the pore size is bigger than the drip irrigation, you may not be bothering much on quality aspects. So, and then there is a subsurface irrigation, like in case of drips, subsurface drip. So, that efficiency will be more compared to surface drip. So, this is the broad classification. The best method, if you are talking, if you have that is a tough question based on your water source availability. So, if you have lot of water, so you do not want to invest in pressurized irrigation. So, you can directly use gravity irrigation, like either furrow irrigation. Furrow irrigation is making channels and delivering water, conveying water at the one end, and waiting to infiltrate to the required depth. So, that is the way in case of surface irrigation, furrow irrigation could be the more efficient one. And whereas, in case of pressurized irrigation, I mean, if you have limited water source, and you can and the governments are really encouraging to go for irrigation, like pressurized irrigation systems like drip and sprinkler. So, drip irrigation, so you can go with subsurface drip, so that you can reduce the the loss of pipe, loss of laterals due to rodents, if you have a lot of problem in the fields. So, so subsurface drip could be efficient one in case of pressurized. So, any other questions you have? Yeah, so I am doing research. Could you please explain me how to measure hydraulic conductivity of soil in a paddy field? Okay. So, the hydraulic conductivity, so basically is a coefficient in Darcy's experiment. Okay. So, that means if you have a saturated column, see the water which is passing through, the flow of water which is taking place from the saturated column, we assume that the steady state. So, then the flux will be equal to the constant multiplied by the hydraulic gradient. So, hydraulic gradient basically decides the flow, the velocity. And then, so in case of the question here is how to find out hydraulic conductivity in case of paddy fields. So, the paddy fields, if you see, so initially the paddy soil, the top soil, so 20 to 30 centimeter soil will be puddled. So, that means that the puddling soil, the puddled soil will have is mostly contains a lot of clay and silt, and then so the hydraulic conductivity will be less, and also it is creating the plow sole at the bottom. So, that means it is a kind of saturated soil stratum sitting on the impervious layer, that is a plow sole. So, in this kind of situations, how to find out the hydraulic conductivity. So, since it is a saturated soil, so you can consider, if you take one section, the top to bottom till the plow sole. So, this could be acting like a saturated soil column where we see in Darcy's experiment. So, assume that you have the piezometers. Piezometer is nothing but a pipe having entry point at the bottom. So, if you install the piezometer at two depths, so just like if you see in case of what is that? This is a new, it is not coming. Okay, just like in case of Darcy's Darcy's experiment. So, the top you are going to supply water, and bottom you are expecting the flow Okay, so then okay, so if you see here, so let us say this is the soil and this is the ponding water in case of paddy field, and let us say this is the plough soil. Okay. So, install one piezometer here, right, and you can also install another piezometer down here, let us say. So, you want it all depends on which soil stratum you are able to you are trying to find out the hydraulic conductivity. Suppose you want to find out hydraulic conductivity of this stratum. Okay. So, at this point and at this point, let's have two piezometers here. Okay. So, you can monitor the water levels in the piezometers, the two piezometers, and knowing the, suppose the piezometer, the water level in piezometer this and water level piezometer this, and the difference will be delta H, you can consider. Okay. And then, so let us assume that the flow is taking place, assume that this is the leakage basically. So, because the flow is very very minute. So, then, so what happened, this is the delta H and that this is the distance between the 2 points, that is delta L, and so the and if you know the the daily water levels, the difference in water levels, let us say delta H, this capital H, let us say. So, delta capital H is the loss, so which is taking place here, and let us say there is a K, and then you have the difference delta H by delta L. Okay. And suppose so here delta H is depth units. If you can multiply with the area of cross section. Okay. So, area of cross section, and because this is the daily time step. So, that will be the during the day how much flow is really taking place, and then with this formula you will be able to find out the K, you can substitute the values. Okay. So, that way you can know the daily hydraulic conductivities, and also you can see how the hydraulic conductivities of this particular stratum is going to change during the season, because of there is a plant, there is a plant. So, the plant has root system, everything. So, definitely we expect the hydraulic conductivity may change because of the macro pore generations and all the other things. Okay. So, this is the simple explanation to find out how to estimate hydraulic conductivity for paddy fields when during season, and also you can try similar kind of experiment during half season. I mean removing the plant, and you can use lysimeters. You can also use, if you have a lysimeter, that is a tank. Okay. So, then you can use I mean this is open type lysimeter. There are the 3 types, I think I explained in the lectures. So, if you have bottom open with crop, bottom closed with crop. So, if you have this setup, then you will be able to find out what is deep percolation, and deep percolation the information, deep percolation is nothing but here the delta H, the flow, I mean the flow. So, the discharge will be known, and then you can find out I mean you just install the piezometers at different depths, and then you will be knowing you will be estimating the K value for in different cases. So, we got another question here. Maybe I will go for the next screen. Yeah. Oops. Next page. Okay, the question is, I have doubt related to ET. So, evapotranspiration he is asking. So, my questions are what is ET and how is ET measured? Okay, so yeah, so what is ET? ET here we are talking about is evapotranspiration. Okay, so evapotranspiration it contains, mostly we are talking about the cropped areas, evaporation through cropped areas. Suppose you have a crop which is growing in the field. So, how to find out the evapotranspiration? That means the water loss through the plant as well as the water loss through the unplant surfaces. So, like soil, and if you have a water bodies and then the water. So, evapotranspiration basically contains two parts, evaporation and transpiration from the body of the plant. Okay. So, since it has two parts, and how it is measured. So, it is measured, I think I explained just now, I also explained using lysimeters. So, if we have three suppose lysimeters and one is no crop, open, I mean bottom open, and the other is with crop, bottom open, yeah, and other one is crop without bottom open. Okay, I mean closed, bottom closed. Under these scenarios, in the first case, if you in the three cases, if you find out the differences, if you find out the water depths, the daily change in water depths, so that signifies the loss. So, in first case, that means the water, the lysimeter, which is bottom open lysimeter. So, so the only possibility of in this case is both evaporation plus in case of bottom closed without crop, the only possibility is evaporation, and suppose bottom opened and no crop case, it is evaporation plus depercolation. Okay. And the other case, bottom closed bottom opened and crop case. So, you have the chances of like depercolation, evapotranspiration. So, the loss is due to depercolation, evapotranspiration. So, in the first case you got you saw the differences. Okay. So, if you take the difference of either case 1, case 2, case 3, case 2. So, you get the difference will give the evapotranspiration basically. So, that is lysimeter based approach, and you have the well defined formulas to estimate reference evapotranspiration. So, you have weather data. So, based on the weather data and available parameters. So, there are number of equations available, for example, Penman-Monteith equation, Hargreaves equation. So, there are several. So, you can use any of the method using the weather data, you will be able to find out ET0, that is reference evapotranspiration. So, knowing the reference evapotranspiration and knowing the crop coefficient. So, the particular crop has different coefficients, which is already tabulated by FAO, that Food and Agriculture Organization. So, with that Kc value, if you can multiply with ET0, you will be able to find out ETC. Okay. So, the evapotranspiration in the field, that could be actual, this could be potential. Okay. So, the actual field, actual evapotranspiration, what we expect is due to the different stresses. So, you may be not irrigating sufficiently. So, I mean that is that is actual evapotranspiration. So, the evapotranspiration which is obtained in a crop field where the irrigation may be the limited. Okay. So, or maybe the crop or growth may be the limited condition due to nutrient stress and other things. So, that is the actual evapotranspiration, and whereas potential evapotranspiration, where you supply for the crop, you are giving enough amount of water, the sufficient water as well as nutrients, so that the growth we expect is maximum as well as the yield is expected to be maximum. That is a potential yield, that is a potential evapotranspiration. So, and then the next question is, what is infiltration and how it is measured in the field? Okay, so the infiltration, okay, the infiltration here we are talking about is how I mean the water can infiltrate vertically down. So, it is like a downward movement of water from the surface I mean surface of soil to the subsurface. Okay. So, this infiltration process that will indicate how fast I mean the water can penetrate into the soil. So, that is very important in case of irrigation, because in case, especially in case of surface irrigation, because in surface irrigation you deliver water at one end and expected to reach the waterfront advance at the other end, meeting the irrigation I mean requirement. So, irrigation requirement here what we are talking is the infiltration depth. So, that is a desired infiltration depth. Suppose whether the water which is really reaching the crop root zone or not during the irrigation operation. So, here the infiltration rate definitely influenced by the both fluid as well as the media property, like the soil properties. So, soil, if you have the sandy soils, so the water infiltration will be faster compared to the clay soils, and also if you have like the quality of water. So, you have a pure I mean irrigation water like a waste water versus nominal irrigation water. So, waste water contains colloids and other things, so that may clog the pores and the infiltration rate will be decreased in case of waste water. And then and you have like the viscosity, water viscosity, so or the water temperature. So, all these things are going to influence the infiltration rate, and this infiltration is being measured we call it a point measurement. So, using ring infiltrometers, so simple. So, it is like a single ring infiltrometer, or also you can use double ring infiltrometer. So, single ring infiltrometers are okay in case of sandy soils, because we expect the flow is vertically down. That is what infiltration means. So, suppose non sandy soils, what happens, there will be lateral flow. So, the amount of water which is going down may not be representing the infiltrating water. So, that is why you have to use the double rings, so that the lateral movement of water can be nullified, or you can say avoided. Okay. So, in case of non sandy soils. So, you can use single ring and double ring infiltrometers. Also, you can use inflow outflow method in case of if you have furrow irrigation. So, what you can do is, so you will be for say take a single furrow and find out the inflow and outflow discharges. So, Q out minus like a Q in minus Q out will be the water which is the storage water divided by the length, the discharge divided by length is a meter square divided by second, and if you can divide that with the width. So, you will be able to get the vertical movement of water in case of I mean this is inflow outflow method. And there are other infiltrometers also available. You can use directly in situ infiltrometers, directly you can get the values. And what else, you can also use some softwares. Okay. So, some softwares are available, you can find out the infiltration parameters, and then from there you will be able to estimate how much water is being infiltrated for a particular soil type. You have any? There is another question. What are different types of soil moisture? Okay. So, the soil moisture, as initially talked about it. So, when the soil is soil pores are completely filled with water, we call the saturated water. So, and then in the field what happens, that saturated water, that is field water. So, and because of the gravity, so the water which is freely moved due to gravity will be escaped. Okay, so that is a gravity water, and then some water which will be left within the pores, so that water is not influenced by gravity. So, that is we call the water at field capacity, the moisture at field capacity. So, if you see the pressures, I mean these are the moisture contents, and then there are several like withdrawals might be taking place. One could be due to evaporation, one could be due to plant uptake. Okay, so, there will be soil water loss which is taking place, and then so then the moisture will be reduced, that can hit the permanent wilting point. So, where I mean the plants cannot extract anymore from the soil pores. So, that is the level, and then there is a residual moisture content. I mean residual moisture content, even in the dry case only you can estimate using oven dry method. So, that is the residual moisture content even less than the wilting point. So, the moisture, soil moisture is related with the metric potential. Okay, so, initially if you see the soil particles are held by I mean the water is filled with soil pores, filled by soil pores. So, what happens initially if you take the pressure, so generally the tensiometers are being used to measure the the pressure. So, in saturated case generally we get the the pressure is 0 or up to maybe 10 millibar, 10 to up to even 100 millibar you can get. And then the field capacity 100 millibar to around 300 millibar. So, the field capacity range, then after that you have like 300 beyond, even 10,000 millibar we expect the wilting point. Okay. So, like that. So, I mean this moisture and pressure has some relationship, we call that is the soil moisture characteristic curve. So, you I mean for a particular soil you will be able to first initially you have to get the soil moisture characteristic curve. So, that you will know at what I mean the soil is, I mean at what pressure the soil is present and what soil moisture the soil contains. So, in order to know that, the soil moisture characteristic curve needs to be generated. So, that can be obtained by taking soil samples, and then in the field like pressure plate apparatus could be used to get the soil moisture at the different metric potential levels. Okay. And this is I mean this is soil moisture, but if you are talking about soil waters, I mean this is irrigation point of view, but if you are talking about soil waters. So, I mean from top to groundwater level, the different levels of soil moisture or soil water are available. So, first one top the soil water we call, and below that we call this intermediate zone, this unsaturated zone, and then there is a capillary zone and followed by groundwater zone. So, groundwater zone basically is saturated zone, and above that till soil water zone it is called unsaturated zone. Okay. So, So, and then so the mostly, so the weather zone, which is a connection between soil water zone and the groundwater zone. So, because that is a critical, and also that acts like a filter. Okay, so that acts like a filter. So, water which is passing from soil water zone to groundwater through this weather zone. So, weather zone is kind of a filtering unit, and you have okay. So, there is infiltration and percolation. So, are they refer to the same process? So, that is the question. So, infiltration, as just I explained, it is a downward movement, it is a downward movement, and it is I mean confined to your soil water zone. So, then after that, if still the water is passing through the other zones, like intermediate zone and then capillary zone, it's finally it is going to the recharging to groundwater. So, here the percolation is the leaching process, or the water which is connecting the soil water zone to groundwater basically. So, the leaching water from soil water zone reaching to groundwater is called the percolation process, due to percolation process. Okay, so these are some of the questions, and then we see we expect few more questions in the next few minutes. Otherwise, we were initially talking about the water lifting devices. So, the lifting devices, as I said, you can lift water from 3 different sources. One could be from the groundwater, the other could be underground reservoirs, and then from the rivers. So, these from 3 so water sources you need to lift water. So, and again I talked about how the broad classification. One is indigenous water lifting devices, and then the pumps. Okay, so these water lifting devices are worked on different principles. The first one is the direct pumping or direct lift, you can say. So, the direct lift in the sense, just like if you have bucket of water and taking water from a mug, it is a direct lift. Okay. So, there are some water lifting devices. For example, you have a scoop. Scoop is a indigenous water lifting device. So, that has been used for several years. So, it is a very simple device. So, it has at the center is tied with a rope, the other end will be used by a person. It is like dipping the scoop into the river and then just dropping the water into the field channel. So, that is the direct lift. And the second principle is a positive displacement. So, in case of positive displacement lift, water is lifted from one level to the other level. So, without losing water. So, for example, you have what you call this lift pump. So, in case of lift pump, so for one stroke some water will be getting into the cylinder, and the next stroke, so the water which is filled in the cylinder will be delivered or discharged. Okay, so, every time you will be lifting a fixed amount of water. So, that means you are displacing water and then the new water pocket is going to come in. So, based on your number of in and out strokes. Okay. So, this is positive displacement. And then third principle is creating velocity head. So, creating velocity head, suppose the water is under quiescent condition, and within water there is an rotating axle. So, what happens if the axle rotates continuously? So, the water which is nearer to the axle will be rotate faster. That means the velocity of fluid, rotational fluid will be faster compared to the fluid at the far from the axle. So, when the velocity increases, what happens? The pressure decreases. So, pressure, so that means the low pressure will be generated in the middle. So, that low pressure is going to draw extra fluid, and that will acts like displacing or discharging the fluid from source to the field channel kind of thing. Okay. So, it is like using velocity head, you can create low pressure, and the low pressure draws the water. So, this is another example of velocity head. And then the fourth one is creating buoyancy. So, creating buoyancy in this buoyancy using gas. So, when you pass gas into the fluid, it creates the bubbles. So, the bubbles because that is a low density. So, the bubbles are going to form on top, and that is going to displace water from one level to another level. So, this is one technique, and then the other principle could be the water hammering. So, water hammering case, what happens? So, there is a nicely running fluid, all of a sudden there is a disturbance. So, that creates the hammer. So, the hammer creates the receding wave. So, that means suddenly the fluid will be compressed. It is an of course, it is an uncompressible fluid. So, compressed in the sense it has to pass, it has to escape. So, I mean best example and which this water hammer principle the device will be working is the ram, hydraulic ram. So, in hydraulic ram this the source is located little higher elevation than the pump. So, the water will be, because of the slope, the water will be passed or directly hit the the waste wall we call, and during that process some water will be escaped and some portion of water will be receding back and accumulated inside the air chamber. Then once it is gone inside, that means in the top in the air chamber there will be the pressurized air. So, the air is going to push the fluid down, and then since the bottom is closed by wall, so the fluid, pressurized fluid will be escaped through the side outlet. So, that will be rising or located in the topmost point or high elevated point in the whole system. So, that means you can lift water from one place to the higher elevation without using electricity. So, it works on 24 hours on water hammer principle, and then only disadvantage here is only you can deliver or discharge 10 to 20% of the source water, and since it works 24 hours you need storage tank to store the water. Okay. And then we have any questions? No questions, right? Okay. So, this way based on these principles, I mean all these water indigenous devices as well as the pumps are going to work. So, some of the indigenous devices. So, indigenous devices are basically grouped into three. One is low head device, medium head device, and high head device. So, low head generally it is less than 1.2 meter, and medium head it is 1.2 to 10 meter head, and high head device that means greater than 10 meter head. Okay. So, in the low head case the examples could be scope, oscillating trough, or swing basket, or Archimedean screw. So, all these come under these low head cases, whereas Now these are mostly the man operated, and medium head case. Medium head case could be the buckets, rope and pulley bucket, right, and you have Persian wheel. So, all these things water wheel will come under medium head. I head is rope pulley bucket mechanism. So, it can mostly use for domestic water supply, because the bucket volume will be less, like 7 to 10 liters. So, it will be less for irrigation purpose. So, and then the pumps could be classified as two types basically. One is positive displacement pump and variable displacement pump. So, in positive displacement pump we ensure that there is a fixed amount of water, water will be transported, whereas in variable displacement there could be a loss, so that because of that, and also the discharge will definitely vary with head. So, it is inversely proportional. So, you have, if you increase the head, your discharge will get decreased, but in case of positive displacement pump, they are directly proportional. So, that means head does not influence on the discharge basically. So, even if you increase the head, so the discharge will be the same, okay, in case of positive displacement pump. So, and positive displacement pumps are again classified into your what do you call reciprocating pumps, rotary pumps, and so reciprocating pumps again classified into lift pump and force pump. In case of variable displacement pumps, that the centrifugal pumps, propeller pumps, mixed flow pumps, jet pumps, then air lift pumps. So, these are different classification. And then if you centrifugal pump basically is the most commonly used even irrigation as well domestic pumping. So, the basic principle in case of centrifugal pump is, so one of the principles is creating velocity head that we explained a few minutes ago. So, what happens initially if you observe the centrifugal pump, so it has basically three parts. One is the suction, and then pump unit, and then delivery point. Okay. The suction and the pump unit has basically the casing, and then in the middle you have an impeller. So, initially what we expect in the beginning of the pumping, so we do priming in this sense, filling the suction and also filling the pump unit with water. So, that means the pump unit has completely water, that means the impeller is submerged in or submerged by water. So, then when you turn on the pump, the water which is present in the pump unit, that means along with impeller. So, impeller, because of the rotational force, the fluid is going to rotate, and that creates the low pressure at the center. Okay. So, the low pressure is going to draw fluid from source to the delivery point. Okay. So, this is an example. This is the main principle. So, it has two kind of pumps. One is volute type and the diffuser type pumps, and there is a turbine pumps also. So, volute type, the casing, so that will be volute in shape, and you have different types of impellers. So, impellers could be open type, semi open, the closed type, okay. Then clogging type impellers. So, those impellers, so based on that impeller will be in the center, but the casing, the volute type, so that the fluid can deliver with a less the frictional losses in case of that is a volute type. Okay. So, you can decrease the basically the frictional head, and there is another type called the diffuser type. So, using a diffuser between casing and the impeller will help in increasing the head. So, that is the purpose, and there is a turbine case. So, mostly we will be using these turbine units in the submersible pumps. So, it could be like a multi-stage, single stage things. Okay. If you have a single impeller, that is a single acting kind of thing, and if you have multiple impellers, it is a multiple submersible pump, something like that. Okay. And then so in this pump, I mean when you estimate the power required to operate the pump, so there are several components. So based on your source, whether it is available below the center line of the pump or the source is available at above the center line of the pump. So, all decides your the head. Okay. So, the head will be the static suction head, total static suction head, static discharge head, total static discharge head. Okay. So, you can combine these suction and discharge heads, and that will give you the total head. So, and in each head case as well especially in the pumps. So, we have to consider the three heads. One is basically the potential head. So, the second is the frictional head, and third is the kinetic head. So, kinetic head is the velocity. So, the potential is the pipe length is the potential what we, and second is the frictional, and third is the velocity. So, these three components we need to combine in order to find out the head in a particular unit. Okay. So, once you know the heads, you combine and get the total head and multiply it with the discharge, then there is unit conversion, you can get the HP, like water horsepower. So, knowing the water horsepower at one hand, and you are going to estimate the shaft horsepower by dividing with efficiency terms, and then input horsepower, and finally you get the total horsepower required, and then find out the total power required, and then find out the electricity required. So, this way you can estimate the cost of pumping for a particular duration. Okay. So, there is a question, can you please explain soil moisture characteristics curve, how can it help us in irrigation? Okay. So, I think this question is related, already I talked about this question some portion. So, now how it is related to irrigation, how we can use this characteristic curve in order to irrigate. That means, here how to schedule an irrigation. The irrigation scheduling will have basically three entities. The first one is when to irrigate, and how much to irrigate, how to irrigate. Okay. So, one is quantity and time, then the device basically. So, then how this soil moisture characteristic curve will help us. So, for a particular soil type, the soil moisture characteristic curve will be developed. So, how do you develop? We already explained using pressure plate apparatus. So, you take the soil samples, real soil samples from different depths, and then find out, using the laboratory experiments, you will be able to find out for a particular soil moisture what is the pressure. So, this is the pressure metric potential versus the moisture content. So, basically irrigation when you are talking about irrigation, our criteria is to keep the soil moisture under field capacity. Okay. So, either in the field, if you have either soil moisture probe or the soil moisture tension probe like tensiometer. For example, you have installed a tensiometer in the field. Okay. So, the tensiometer will tell you the potential, okay, the tension, soil moisture tension. So, knowing that you use the soil moisture characteristic curve. So, it has a relationship between the pressure and then moisture content. So, you will be knowing the corresponding moisture content for the soil moisture tension. So, knowing the soil moisture, our aim is to refill the water soil water back to your field capacity. Okay. So, knowing the current soil moisture content and knowing the field capacity. So, you will be able to find the how much water really required to refill. So, that way you can use the soil moisture characteristic curve in irrigation. Okay. So, I think this session is going to end in a few seconds. I hope you got all the answers, and we are going to have another, this is the final session, going to be a final session, that is in October. So, we are going to expect few more questions from you, and I hope you are enjoying the course. So, till then, bye bye, take care, see you in the next session. Thank you.